So before we get started in Chapter 7 today, I want to quickly review some of the stuff from Chapter 6, right? So we were talking about SN1 and we were talking about SN2 reactions, right? Distinguish those for me, please. What's the difference between an SN1 and an SN2 reaction? All right, so two-step for SN1, one step for SN2. What else? Okay. Okay, so that's right. So the rate is proportional, that's an R, I'm sorry. Proportional to a rate constant times the concentration of the alkyl halide. The nucleophile doesn't come in, right?
The nucleophile is that M nucleophile.
Okay. What else? Okay, strong nucleophiles. What about over here? Weak nucleophiles, right? Polar protic solvents. And over here? Anything else? Okay, so partial inversion of stereochemistry or racemization. And what did you say here, Gabby? Complete inversion, right. All right. Good. SN1 stands for substitution, nucleophilic, unimolecular, right? And SN2? Nucleophilic, bimolecular. That's right. Okay, good. So we are going to go into Chapter 7 today, and we're going to start talking about elimination reactions, which kind of started at the end of Chapter 6. I've just thrown all that information together and made it, put it in Chapter 7 because it's really kind of repeated information. So today we're going to start talking about elimination reactions, which can give us alkenes. And we're going to talk a little bit about restricted rotation of alkenes, and we'll start talking a little bit about the mechanism of the elimination. Okay? What ties Chapter 6 and Chapter 7 together? What is the common thread between both of those chapters? Not the mechanism, actually. Although there are similarities, I wouldn't say that the mechanism actually ties it together. What's the substrate in Chapter 6? The starting materials that we were talking about. Alkyl halides. So alkyl halides can undergo nucleophilic substitution reactions. They can also undergo eliminations. Okay, so alkyl halides can undergo nucleophilic substitution. They can also undergo elimination reactions. And so that's the common thread between these two chapters, is that Chapter 6 and Chapter 7 both are going to involve, not exclusively, but both are going to involve the use of alkyl halides. And so we'll just go ahead and get started. So if we start off with an alkyl halide, we can actually treat this with a base and allow a elimination reaction to occur to where we get a new alkene as a product plus the salt of the base. Okay? Pretty straightforward mechanism, at least as it's drawn on paper. Notice this is an alkyl halide, right? And all bases can also be thought of as, all nucleophiles can also be thought of as bases. So we have to determine whether or not this base is going to function as a nucleophile or a base, right? What's the difference between a nucleophile and a base? That's right. So where is this base reacting? It's reacting at this hydrogen to remove it, right? And so it's not attacking the carbon. And so if it's not behaving as a nucleophile, how would we label it? We would label it as a base, but we'd add another non-nucleophilic. That's right. And there are some bases that all they do is function as bases. They don't really function as nucleophiles, and you're going to need to know those. And you know one of them already. What is it? You're right. Just say it. Tert butoxide, right? So like sodium or potassium or lithium, tert butoxide is a non-nucleophilic base. And why is it non-nucleophilic? Yeah. Yeah, it's got a lot of bulk around it, right? And it can't attack the carbon. It can only remove a small proton, okay? So we'll have to memorize these as we go, but you'll get it, okay? So we're able to eliminate, what are we actually eliminating from the alkyl halide? We're removing a hydrogen and a halogen. So what are we really removing? We're removing HX. So if we're dealing with an alkyl chloride, what are we really removing? HCl. If we're working with an alkyl bromide, what are we really moving? HBr. And if we're working with an alkyl iodide, we're removing HI, right? What are those? Those are acids. So to eliminate an acid from a molecule, what do we need? A base, right? That's how I always remembered it when I was in college. I'm removing a strong acid from a molecule, and I know that acids react with bases. That's how I kept track of that, okay? And so the product's going to be a pi bond. Okay, so we're going to end up generating alkenes. So right now, your toolbox just expanded because you can take an alkyl halide on your roadmap and you can convert them into ethers through SN1 and SN2 chemistry. You can convert them into esters by SN1 and SN2 chemistry. You can convert them into alcohols. You can convert them into azides. Right? You can convert them into thiols. We talked about all those things in chapter 6. And now what do you need to add to that roadmap? Alkenes. Are you starting to see that alkyl halides are kind of an important functional group? Right? We can do an awful lot with them. Right? We can do an awful lot of chemistry with them. And so now we know we can do SN1 chemistry with them, we can do SN2 chemistry with them, and we can do elimination chemistry with them. So we can do a lot with alkyl halides, and they end up being very, very important industrially and academically because they are so versatile. Okay. So, for example, here we have what kind of alkyl halide? We have a bromide. That's right. What kind of bromide? Is it primary, secondary, or tertiary? It's primary. Okay? Now, if Delaney came into the lab to run that particular reaction, when she wanted to do an elimination, she better make sure that the base she uses can't function as a nucleophile, right? Because if it functioned as a nucleophile, what chemistry would probably occur? SN2 chemistry, right? So what kind of base did she pick here? Yeah, a big bulky base, right? And can it function as a nucleophile? No. So primary alkyl halides, you're going to want to make sure your base is big and bulky, okay? And in fact, in doing this, she ends up eliminating the hydrogen and the bromine to get the alkene. Where is the hydrogen located in the alkyl halide that must be eliminated? It is on a secondary carbon, but where is it at in relation to the halogen? Right beside it. Okay, and so it turns out that the carbon atom bearing the halogen, we call that the alpha carbon. So what would the next carbon over be? The beta carbon, that's right. So this is also known as a beta elimination. Notice the hydrogens out here at gamma and delta, they're still in the product. They don't get eliminated. It's the beta hydrogen to the halogen, okay? So you're going to hear me use terms like elimination, beta elimination, and I use them interchangeably. You need to know what they mean, okay? But that beta part in beta elimination tells us where that hydrogen is coming from, right? And since we only have one beta carbon, right, it's pretty easy to determine which hydrogen has to be lost. It's one of these two hydrogens on the beta carbon, okay? And we just show these two. So we're eliminating HBr.
Does it matter which one?
It does, but we're going to get to that later. And it only really matters when you have constrained systems, like rings and things like that. But yes, is the short answer. The longer answer is more details to come, okay? How about here? What do we have? I have a secondary alkyl halide. What can secondary alkyl halides do? They can do SN1 or SN2, right? But do they do it as well as, do they do SN2 as well as primary? No. So what can you tell me about the base that they chose here to do this reaction? Is it bulky? It's more bulky than hydroxide, I'll give you that. But would you call it a really bulky base? It's not, right? But yet we can get this reaction to go, right? Because this is not as good at SN2 chemistry as the primary, okay? So we can get away with this. What might you expect to be a side product of that reaction, however? Terry runs this reaction and then she goes and analyzes the products and she sees the alkene and she goes, hey, there's something else in there too. What might you think that something else would be? Not an alcohol. Well, now there will be an alcohol because of how the reaction works. But I'm talking about in terms of this. What else would we get? An ester? An ether. That's right. Because this could also do SN2 chemistry by attacking that carbon and the leaving group leaving, right? So she would expect to see alkene plus maybe a little bit of the ether product, okay? How can she favor the elimination over the ether formation? In this exact reaction, what could she do to try to increase the amount of elimination chemistry that she gets to occur?
Use a polar A solvent.
Okay, polar A protic is going to favor SN2, right? As far as we know right now. So she probably wouldn't pick a solvent yet. We will get to that later. What's one of the easiest things for you to do in the lab? Temperature. That's exactly right. And it turns out that if you increase the temperature, you almost always favor the elimination over the substitution. Are there exceptions to that? Sure. But the rule of thumb is that if you want to ensure the elimination chemistry to occur, raise the temperature. If you want to ensure that the SN2 chemistry occurs, lower the temperature. Okay? So you might actually conduct this reaction at a little higher temperature than normal. Okay? Now, the general features of the elimination that we have here, okay, notice the curved arrows. What are these curved arrows telling us? All right, so describe to me in words how the electrons are moving.
The base
You're right.
reacts with the hydrogen.
Okay, so the base is attacking the hydrogen. What else?
So the hydrogen gives up some of its electrons to the carbon.
Okay, to form what? To form the pi bond. Very good. So these electrons are moving in between the two carbons to form the pi bond. And what else?
Then the beta carbon has to give up some electrons to the
Okay, so but that would be the alpha carbon, because that's the one with the halogen. So that's right, we're breaking the carbon-halogen bond. As this is drawn, how else would you describe that? Is it occurring stepwise or non-stepwise? In other words, is it concerted or is it multiple steps? Is it, as I have it drawn? It's drawn as a single step. It's drawn as a concerted reaction. What does that mimic that we learned about in chapter 6, where everything occurs in a single step? SN2, right? So what do you think the rate of this reaction is going to be dependent on? Okay, but would we call it a nucleophile here? The base and the concentration of the alkyl halide. That's exactly right. The E2 reaction and the SN2 reaction have the same rate expression, except we wouldn't write in the bracket nucleophile, we'd write B, or base, or whatever, right? But we wouldn't call it a nucleophile because of how it's reacting, okay? What else can you tell me about? So, Terry, you asked a question about, does it matter which hydrogen? Does it matter here? Obviously, there's only one hydrogen, right? So it's going to take that hydrogen, but can you tell me something about how that hydrogen is situated with respect to the halogen? If I look around this carbon-carbon bond right here, how is the hydrogen and the halogen with respect to one another? Mm-hmm. They are exactly like trans, right? Notice that the hydrogen is on the opposite side of this plane, if you will, than the halogen, okay? So these electrons that are coming from this carbon-hydrogen bond are attacking by going on the backside of that carbon-halogen bond, right? Very similar again to what reaction? SN2, okay? So you're not really learning a ton new here, right? It's just a different product that you're getting, okay? And so we're going to get this new pi bond, and pi bonds are important because we can do a lot with alkenes. For those of you in polymer science, what do you do with alkenes? You make polymers out of them. You polymerize them, right? Polyethylene, polypropylene, right? Polystyrene. These are polymers of alkenes. And you can actually use elimination chemistry to make new alkenes, new monomers to do new chemistry with, okay? This reaction, since we are eliminating hydrogen and a halogen, is also known as a dehydrohalogenation reaction. A lot of nomenclature here. We can call it a dehydrohalogenation. We can call it a beta elimination. We can call it just an elimination reaction. Okay, there's a lot of different ways to call it. Okay. Some common bases that you need to kind of have committed to memory for this. Sodium and potassium hydroxide certainly work well for dehydrohalogenation. Not as well if we're talking about primary alkyl halides, but for secondary and tertiary alkyl halides, they work really well. Why did I say that? Why not so well for primary and secondary? Or primary, excuse me. They can also function as a good nucleophile, right? So you can end up with a mixture of products there. The alkoxides are also good. These, you may have to worry about SN2 type chemistry, but how about here? So, but all of these are used to an extent in dehydrohalogenation reaction. We're going to learn about two other bases, I hope, today as well that are used. But, you know, these bases right here, you all learned about these in Gen Chem, right? Those are pretty straightforward. These, however, probably didn't. So you need to work on committing those to your memory as well. Okay? Now, in this example, okay, notice we have our alpha carbon, and we have 3 identical beta carbons. So Terry, does it matter where we get the hydrogen from? If the 3 beta carbons are all identical? It doesn't matter, does it? And so we just chose this one to show that we're losing this hydrogen and this bromine. But if we were to lose the hydrogen from here and here, or excuse me, from here and the bromine from here, we'd end up with exactly the same product. We couldn't really tell, right? So why is it okay in this particular case that we use sodium hydroxide as the base? We only get this alkene. We don't get any substitution. Why is it okay here? Because I have a tertiary alkyl halide. That's exactly right. Can they do SN2 chemistry? No. They can only do SN1 chemistry, right? And SN1 chemistry is favored by strong nucleophiles or weak nucleophiles? Weak. Is that a strong or a weak nucleophile? Strong. So what does that tell me about strong bases? Is it going to favor nucleophilic substitution or elimination? Elimination. That's right. Now, if only life were this simple, all beta carbons being identical, makes life real easy, right? However, if we look at this example right here, notice I have 2 different beta carbons. Chance, tell me why those 2 beta carbons are different. Why is this different than this? Okay, and so it makes this carbon a what kind of carbon? Oh, this one's primary, right? This is a CH3, so it's attached to only one other carbon. What about this one? It's a secondary carbon, that's right. And so we could eliminate one of the hydrogens from the primary carbon and the halogen and get this carbon-carbon double bond, which they're calling this one beta 1. Or we can eliminate the hydrogen from beta 2 and get this alkene. And these are constitutional isomers to one another, right? Do they have the same physical properties? No, they do not have the same physical properties, do they? They have different physical properties. Do you think we form those two alkenes in equal molar amounts? No. Can anybody tell me which one we form in greatest amount? This one? Why would you say that? Okay. Because it's big and bulky, right? Not a bad thought. Okay? And in fact, we can selectively get one over the other, and we'll talk about that. And so you do have to look at how big the base is. Okay? You're going to hear terms like Zaitsev and Hoffman and some things that we're going to learn in this chapter. Okay? You're just going to have those committed to memory when we get to them. All right? But we do not have to get these two alkenes in equal molar amounts. Okay? So, I want you to recall that an alkene, what's the hybridization of the two carbons? They're sp2, right? So they are about those carbons. The geometry is tetrahedral? Trigonal planar, that's right. And we have the two p orbitals on each carbon atom, and they bond, right? And so we have two electrons in that pi bond. And so when we build a model of an alkene, can I freely rotate around that carbon-carbon bond? Why not? Okay, so if I take my model and I try to rotate it, what happens to my model? It'll break, right? And so you'd have to break a bond to do that rotation. When we rotate around a sigma bond, am I breaking any bonds in doing that? No, because it's cylindrically symmetrical. I had to think about how I was going to word that, right? And so by doing this around a single bond, I don't have to break anything, do I? But if I have a single bond, or a sigma bond, if you will, and then the pi bond, if I want to rotate around those two carbons, what has to happen? I have to break one of those bonds. And which bond do we break? The pi bond. And all bond breaking events, what? Endothermic or exothermic? Endothermic. All bond breaking events require energy. Remember, for those of you who've had biology and they say you get energy out of breaking the ATP bond, that is not true. All bond breaking events require energy. Okay? There is no such thing as high energy bonds. Okay? You break a bond, it requires energy. It's an endothermic process. And since it requires energy, does it occur freely? No, not at all, right? Does that mean I can't rotate around a carbon-carbon double bond? No, but in doing so, I have to break the bond first before I can do the rotation. There are ways to take an alkene, break the pi bond, and have it reform again in a different conformation, okay? Cis and trans isomerization of alkenes can occur, okay? But it requires energy, usually light, for that to happen, okay? So, there are multiple types of alkenes we can get, right? We can get monosubstituted, where we only have, if we look at the carbon-carbon double bond, right, we only have one R group attached to it. These are monosubstituted alkenes. They're also known as terminal alkenes. Why would we call them terminal alkenes? That's right. If we counted the carbons through the chain, right, they are at the end. That, you know, we would start numbering at carbon number 1 here at the terminus, okay? We can have disubstituted alkenes, where the carbon-carbon double bond has 2 R groups attached to it. Now here we just have the 2 R groups attached to the same carbon, but is that necessary? No, we could actually have them attached to different carbons of the alkene as well. We can have a tri-substituted alkene where we have the alkene with 3 different R groups attached to it. And we can have a tetra-substituted alkene where we actually have 4 different substituent R groups attached to the alkene. Okay? Now these substituents can be either part of a chain like we have here. This is monosubstituted, right? We can have a disubstituted alkene where we have the 2 R groups being part of a ring. That's perfectly fine. And here we have a tri-substituted where we have one of the carbons being part of a ring like this, so that's 2 substituents, and then this other substituent here at the end, okay? So we can have monosubstituted, disubstituted, tri-substituted, and tetrasubstituted. Are they all equally stable? No, they are not. And it turns out that the more substituents you add to an alkene, the more stable the carbon-carbon double bond becomes, okay? So this is just an example of the free rotation that we talked about, and this is butane, of course. We've looked at the Newman projections for that before. We can rotate pretty easily around that carbon-carbon single bond. However, in doing so, there's still energy involved in that, right? Why would we have to put energy in to go from the anti-conformation to the eclipse conformation? That's right. That's higher in energy, right, than that. And I know my hands don't quite do the modeling quite well, but that is higher in energy than that, right? And so we learned about what that energy diagram looks like, right? Now, if we look at 2-butene, I can have 2 different flavors of 2-butene, if you will. I can have the 2 methyl groups on the same side of the plane, and we call that cis. And I can also have those 2 methyl groups on opposite sides of that carbon-carbon double bond plane, and we call that trans, okay? Which one of those do you think is more stable, the cis or the trans? And why? Okay, those groups are far apart from one another, right? Here, these 2 methyl groups are actually on the same side of the world, if you will, and they start to run into each other a little bit, right? So this is actually higher in energy than this. However, I can't freely rotate around this. I can't just set cis 2-butene in the dark and allow it to interconvert into the more stable trans. However, I can take it to my lab. I actually have a lamp called it's a mercury arc lamp that actually is about as bright as the surface of the sun. You can put that on there, and you can take cis alkenes and you can make them trans. What does that light do? It adds energy. It breaks the pi bond, allows rotation to occur, and then what happens? The pi bond forms again. That's right. Because everything likes to have an octet, right? And you will eventually convert all of your cis isomer to the trans isomer through that process. Okay? So this isn't easy to do directly, but it can be done if you shine some light on it. Okay? But it does not freely occur because you have to break that pi bond. These are diastereomers of one another. So what would you expect for the physical properties? Okay, so Danielle comes into the lab and she wants to know whether she has the cis 2-butene or the trans 2-butene. What might she do to figure that out? Pardon? Heat it up and do what? Okay, so yeah, we could measure their melting point or boiling points. Okay, very good. And we'd just look them up in a table, right? This has a particular boiling point that we could find. What else might we do? What other techniques have you learned in lab that we might be able to do to determine these? IR technically can work, but you're going to be getting down into the kind of the fingerprint region to do that. If you're really good at it, you could figure it out. Distillation, okay, but that would be determining the boiling point, right? That would be one way to do it. Chromatography, what would we see in chromatography? Okay, so maybe this one has a different RF value than this one, right? It's possible, yeah. Probably we wouldn't use TLC. What's the chromatography you all are going to use next week? Gas chromatography, that's right. Because these are actually fairly low boiling. You'd probably inject these on a GC and measure where their peaks come out. and compare them to standards of known retention time. Is another way of determining which one you got.
When you were talking about with those, the lamps and like making them go to the other one, does it favor that one side because they're trans, so it's?
Yeah, you can actually go from cis completely to the trans side. Yep.
Because that's the formation they want to be in because they're further away.
It's the lower in energy. That's right. And it is lower in energy because they're further away. That's exactly right. Stereochemicals. Okay? Whenever the two groups on each end of the carbon are different from each other, you have two diastereomers being possible. Okay? So when we're looking at an alkene, we need to identify the two carbon atoms of the alkene, and we need to look and see what's attached to each one of those carbons. Okay? If on this carbon we have X and X prime, and on this carbon we have Y and Y prime, we can actually have two different diastereomers. We can have the X primes being close to one another, or the X and Y prime, excuse me, being close to one another, or on opposite sides. So we can have cis-trans isomers, okay? So let's look at some examples. What is X and X prime on this carbon? A hydrogen and a methyl group. What about here? A hydrogen and a methyl group, right? But notice there's two different groups on each one of these carbons, right? So this and this are trans to one another. And if we flip two of these, we get the other diastereomer, right? And they're not identical. What if this molecule had two hydrogens on this carbon? Can I have diastereomers? Why not? Can't I take one hydrogen and swap it for the other? I could do that, though, on paper. We're not talking about resonance structures. But it ends up being the same thing. That's exactly right. So when you swap two groups and you end up with exactly the same thing, can you have diastereomers? No, right? But clearly, swapping this hydrogen for this methyl group and vice versa gives me something very different, right? So when we have two different substituents on a carbon of the alkenes, we can have diastereomers, okay? Now, I mentioned earlier that the more substituents you put on an alkene, the more stable it is, and that's what we're seeing here, okay? So we know that unsubstituted alkenes like ethylene are unstable. They readily polymerize, for example. But they are less stable than a primary alkene, which is less stable than a secondary alkene. And notice we have the different secondaries here, okay? And then the tertiary, and then the tetrasubstituted. So, trisubstituted and tetrasubstituted, excuse me. Getting my nomenclature jumbled up here. So if you had to pick something to polymerize, what would you pick? Something over on this end, right? Yeah, like ethylene. What do you think would be very resistant to polymerization? These kinds of things. That's exactly right. And so if you look at all the monomers for the typical plastics anyway that we use, like polyethylene and polypropylene and polystyrene, they're all on this end of the spectrum. They're less stable, and they will readily polymerize, okay? For example. Okay. So if I look at the butene isomers, okay, will you all agree that 1-butene, cis-2-butene, and trans-2-butene are all different? But they all have the same number of carbons and hydrogens, right? All right. How would Paige come into the lab and prove this order? I just made a statement that 1-butene is less stable than cis-2-butene is less stable than trans-2-butene, right? Just okay, so maybe look at some chemistry, right? What will that do?
The ones that are less stable will need less energy to make them switch over.
Okay, all right. You all are talking about the right concept. Think back to general chemistry lab. What did you all do to determine the energy of a reaction or the energy of something? You guys used some coffee cups to do something. Remember that? Uh-huh. Coffee cups and a thermometer and... Pardon? There were styrofoam coffee cups, yeah, and you had a solution, and you had a cap on it, and you had a thermometer. Calorimetry, that's right, measuring the energy of something, right? So now with that in mind, what might she do coming into the lab? She might do some type of calorimetry experiment, right? And if something is less stable, are we going to get more energy out of it when it reacts or less energy? More energy. That's exactly right. The thermometer is going to read a lot higher temperature, right, if you will. It turns out, and you all will learn this when you get to PChem, for those of you who continue on, you can do what's known as bomb calorimetry. You can take these and you can burn them and measure the amount of heat that comes off when you do that, okay? And that's what we're doing here. Notice all of these isomers of C4H8, right? Same number of carbons, same number of hydrogens for all of these. They're going to require the same amount of oxygen to burn. They're going to give me the same products, carbon dioxide and water. 4 moles of carbon dioxide, 4 moles of water. So the floor is exactly the same. The difference is how high in energy each one of these are. And so what Paige would do is she would take the terminal alkene, she would place it in the bomb calorimeter, she would explode it inside there, and she would measure the heat that comes off. And she would find that it gives 17 kilojoules per mole of energy. Then she would take the other isomer, and she would do exactly the same thing. She'd put the same number of moles in the bomb, same amount of oxygen, she would explode it, and she would get the same amount of products. But notice what she measures. Is the energy the same? No, it's lower. Why is it lower? Why is it more stable? Well, that's true. It's closer to this, but why is this more stable than this? That's right. This is a disubstituted alkene, right? And then she does the same thing for the disubstituted that's trans, and what does she notice? Even less, right?
Why is one end more energy than the other one?
Than this one?
No.
Than this one?
Than the one that looks the same as it.
Which one looks the same as it?
The third one.
No, this is a second, or disubstituted. This one is a monosubstituted. Okay. So yeah, it zigs and zags the same way, but notice the position of the double bond is between carbons 2 and 3 here, where here it's just between carbons 1 and 2. That's why. Does that make sense? Okay. So why is this giving up more, or excuse me, giving out less heat than this one? The trans is more stable, right? By about 3 kilojoules per mole, right? And then, of course, we have this disubstituted, and notice it's even more stable, okay? So when we have the disubstitution on the same carbon, we end up with a more stable alkene than when we have these. So you can use that general chemistry, calorimetry stuff you all learned about to actually go in and prove these statements that we make in this class, okay? It's all connected. Now, there are mechanisms to this elimination, and there are 2 mechanisms. Actually, there are 3 mechanisms. We're only going to learn 2, okay? There is E1 and there are E2. Just like you had SN1 and SN2, you can also have E1 and E2. So E2 is a bimolecular elimination, so it is more similar to which of the SN? It's just like SN2, right? So the rate is going to be equal to a rate constant times the alkyl halide times the base, right? And we can have, and how many steps do you think it's going to have? It's going to have 1 step. So as the base comes in and abstracts the hydrogen, the leaving group is leaving and the pi bond is forming all at the same time, okay? With an E1 mechanism, it's unimolecular elimination, so it's going to be very similar to the SN1 reaction, right? What's the rate of the reaction for the E1 going to be dependent on? Which is what? The alkyl halide. That's exactly right. So this is a unimolecular elimination, okay? And so what do you think about, there's got to be an intermediate here. What's it going to be? It's going to be a carbocation. That's exactly right. We're going to have a carbocation that we have to pay attention to, okay? And that's going to be another theme of this particular chapter. We're going to see carbocations. just like we saw carbocations in chapter 6. And actually on Monday, I'm going to do a demonstration at the beginning of class. So make sure you bring something that can record video, your camera on your phone, a camera, tablet, whatever you have, okay? Because it's part of the video project. We'll do that on Monday. And then we're going to spend some time talking about what's really going to cause you all a headache, carbocation rearrangements. So you really need to read on that over the weekend before you come in, all right? So, E2 elimination, it's the most common mechanism for dehydrohalogenation. It exhibits second-order kinetics, first order in alkyl halide, first order in base, and it is concerted. All the bonds are being broken and formed in a single step. Just like in the SN2 reaction, we were forming the carbon nucleophile bond at the same time we were breaking the carbon leaving group bond, right? Same thing, so we call this a concerted reaction. And here's the example. What kind of alkyl halide do we have? It is a tertiary alkyl halide, right? Is the leaving group good?
Yes.
Yes, we've got a good leaving group. It's tertiary. Do I have a good base? Yes. All of those things are going to favor the E2 mechanism. The only difference here is what between this and the SN1, other than the fact that we don't have substitution going on? Can SN1 work on, or excuse me, SN2 work on tertiary alkyl halides? No. But E2 can work on tertiary alkyl halides. So the hydroxide is coming in, removing the hydrogen. The carbon-hydrogen electrons are forming the pi bond, and the leaving group is leaving, all in one step. Okay? And that's how that works. The energy diagram looks pretty much so the same, right? Notice we have a single energy of activation, and what's involved in this step? Both the base and the alkyl halide, right? That's why they both appear in the rate equation, okay? But that looks very similar to the SN2 reaction, doesn't it? Okay. Two other bases that you need to know that are very useful for E2 reactions, okay? Diazobicyclononane and diazobicycloundecane. Do not try to memorize that name. All I care about is that you know DBN and DBU. They are both non-nucleophilic bases. Why might a person want to have this type of a non-nucleophilic base over, let's say, potassium tertbutoxide? Why have multiple tools when one seems to work on paper? Right? Potassium tertbutoxide is a non-nucleophilic base. Why can't we use it all the time? What's the difference between potassium tertbutoxide and DBN and DBU? Tertbutoxide is a salt. What about DBN and DBU? They are not salts. And why does that matter? Are salts going to be soluble in a lot of organic solvents? Highly soluble? Why not? It's a true statement. Why not? Why would you have trouble getting sodium hydroxide, for example, into hexane?
Because they dissolve it, because like dissolves
Like dissolves like, that's right. And salts are very polar, right? Hexane is not very polar. What do we typically do organic chemistry in? Water or organic solvents? Organic solvents. So sometimes we're going to have difficulties getting these salts into solution, right? However, are we going to have that problem with DBN and DBU? And why not? Because they're organic and they are not charged. They are not salts, right? And so that's why we need to have additional tools to do these kinds of things. Now here's where it becomes kind of important, okay? For those of you who want to go to medical school, this is called a prostaglandin. Does anybody know what prostaglandins are useful for? Anybody ever hit your finger or something and it starts to throb and starts to swell? Prostaglandins are responsible for that. Anybody ever run a fever? Prostaglandins are responsible for that. Anybody know anybody with arthritis? Prostaglandins are responsible for that. It's a whole lot of that kind of stuff. That's exactly right. And they're involved in a whole range of other issues. But one of the things that you have to study when you get to med school, you'll study the prostaglandin cascade, and it'll make organic chemistry at sophomore level look like child's play. Okay, because this isn't the only one that's made. Okay, and you need these standards to know what the prostaglandin levels are in biological tissues, and these are made by organic chemists. And one of the ways that they made this was by an E2 elimination of an alkyl halide to put the pi bond exactly where they needed it in an intermediate that was then used to make the prostaglandin. Okay? And they used it using chemistry that you all learn at the sophomore level. Okay? So I'm going to stop here for today.